have already discussed that the discharge over a rectangular weir can be given by the formula which is given below, which says that q is equal to 2 by 3 cd under root 2g L h raised to the power 3 by 2. Now this formula is only applicable when you are not considering any concept of the velocity of approach. So we can write that without the consideration of velocity of approach. It means that you are assuming that the velocity at which the fluid is approaching towards the weir is zero. However, this is not the practical case. So, due to this, the consideration of the velocity of approach is very much important, and due to, or you can say, in order to consider this concept of the velocity of approach, this formula is modified, and which says that the q is equal to 2 by 3 cd multiplied by 2g multiplied by l, and then concept of the velocity of approach should come into the picture using the HA, that is the head produced by the velocity of approach, and the formula which looks like this one. So in order to assess the actual discharge with the consideration of the velocity of approach, this formula should be used. Now it is interesting to note that if we are saying that this is equation 1 and this is equation 2, then both these equations, which is 1 and 2, they do have certain kind of condition when they will be applicable. So using applicability of the equation 1 and 2 is subjected to when there is no contraction. That means we can say that our crest length is equal to the width of the channel. It means, in other word, we can say that there is no contraction in the channel, or you can say weir. All such kind of weir where there is no contraction and the crest length is equal to the width of the channel, such kind of weirs are called as suppressed weir. What will be the situation if the contraction are available there in the weir? So when weir is not suppressed, then the effect of the contraction should be taken in under the consideration. So what we can write is that if the contractions are available at the end of the weir or ends of the weir, because contraction can be either in the one sided or the both sided depending upon the construction. So if constructions are available, then for such situations vs are not suppressed. To overcome such situations, and in order to measure the actual flow which passes through the crust having some contraction in the field, some researchers who have proposed some empirical formulas based on their experiments. So the first formula which is very much popular is the Francis formula, and second formula is the Bazin's formula. These, I mean, both these formulas are the formulas which is based upon the results of the series of the experiments. So this came from the results of a series of experiments. What usually happens whenever the problems are very much complex and we are not able to find out the exact equation, in such situations we all do some kind of experiment, and from the experiment we just find out the our results, or you can say the observations. and based upon the our observations, we just try to make a relationship between the variables which control the output. In this case, we will be looking for the what are the variables which are controlling the q. So the variables would be like L, H, HA, such kind of thing, and then contraction. So based upon these strategy, these scientists have derived the formula. These are very much popular. So in view of the applicability of such formulas, we will going to discuss this, how we can implement and how we can go for the use of these formulas for the assessment of the discharge through a channel which are having some end contractions. So first of all, we will discuss the Francis formula in order to figure out the discharge through the rectangular notch having some contraction. So we are going to discuss the Francis formula. So Francis has concluded based upon the findings of his experiment that the end contraction decreases the effective length of the crest of the weir and hence decreases the discharge of the weir. So if you can see, there is a channel where the end contractions are available at both ends. One end contraction is this location and one end contraction is on this location. So if you see, when water is flowing from touching the end contraction, it is again effectively just reducing the width of the weir, or you can say length of the weir, by the 0.1 into h, where h is the head of the weir, or you can say water head. So this is directly proportional to the head of the water which is flowing over the weir, and the instead of the original length of the L of the weir, the actual length which left is, instead of L, this effective length becomes L minus 0.2 times of H. Now, if H will be very high, so effective length is going to be, or we can say effective length is going to be decrease very sincerely. So here number of the end contraction, and then you multiply by the 0.1 multiplied by the H, and then subtract from the original length of the weir, and then that's how you will be able to get the effective length. So let's start to discuss how we should use this thing for the determination of the discharge. So what exactly is the effective length? You can say that effective length become L is equal to L minus 0.2 H. So instead of writing this value, we should need this value as a LE. So the Q value what we used to write is that 2 by 3 CD multiplied by LE, that is your effective length, and then multiplied by under root 2g h raised to the power 3 by 2. Now you just replace the LE value from the equation 1 into the equation 2. This will look like b q is equal to 2 by 3 CD, and in bracket L minus 0.2 h, and then under root 2g h raised to the power 3 by 2. Now if you put the CD value for such channel is equal to 0.623 and G value is 9.81 meter per second square, the same equation can be simplified as Q is equal to 2 by 3 multiplied by 0.623 multiplied by under root 2 multiplied by 9.81 multiplied by L minus 0.1 into, this is 0.2 H, and then H raised to the power 3 by 2. So this equation will be simplified as, and can be written in as, Q is equal to 1.84 L minus 0.2 H multiplied by H raised to the power 3 by 2. Now, so that is the your final equation. And in actual condition, if there is no end contractions are there, for such condition the This will be called as suppressed weir. So in case of the suppressed weir, the Q can be revised as Q is equal to 1.84 H raised to the power 3 by 2 multiplied by L. So that will be the value of the discharge using the Francis formula when ends are not suppressed. So you can say that this is suppressed weir. Now, if we consider the velocity of approach into the consideration, the same equation can be written as Q is equal to 1.84 into L in brackets H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. Now, if the discharge Q of the water flowing over a rectangular weir with velocity of with the consideration of the velocity of approach and as well as the end contraction, the same formula of the discharge can be written as Q is equal to 2 by 3 CD under root 2 G and in brackets L minus 0.1, and I am writing neta. Neta is giving you the number of end contraction, and then this is H plus HA and then bracket closed, and in next bracket this is H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. Now we have to use this particular equation for estimating the discharge. So this neta is number of end contraction. So this equation is applicable when end contractions are available. Also, you are considering the velocity of approach into the picture. So that's in the discussion on the Francis formula, and similarly there is one Bazin's formula, and let's discuss this one. And similar to the Francis formula, Bazin has also proposed his formula based upon the results of the series of experiment. So the formula proposed by the Bazin is again applicable for the rectangular channel. That you need to remember this thing, that this particular equation is only applicable for rectangular channel, and this formula can be written as that Q is equal to m multiplied by L under root 2g h raised to the power 3 by 2, where m is a constant and that m value is dependent upon. Similar to the Francis formula, Bazin has also proposed the formula of the discharge over a rectangular weir, and which is based upon the findings of the series of experiment. So we need to remember this point, that this particular formula for the discharge over the rectangular weir is to be used. So what we can say, that this particular equation should be used for the estimation of rectangular weir, discharge over the rectangular weir. So what he proposed is that Q is equal to m L raised to, multiplied by under root 2g h raised to the power 3 by 2, where m is a constant which is written as 2 by 3 CD, and that is equal to 0.405 plus 0.003 over h. So this is the constant that we will be using in the previous equation. Now, where h is the height of the water over the weir, that we must know that this is the height of water over weir. So it is interesting to note that m is also the function of the head of the water itself. So if the velocity of approach is also into the picture, then we can, this formula will be modified drastically. So the same equation 1 and 2 will be revised as q is equal to m 1 multiplied by L under root 2g h plus ha raised to the power 3 by 2. You need to remember that this is only applicable when you are considering the velocity of approach into the picture. So this is your equation number 3. So the equation and similarly the m value will also be modified, and that's why we are writing it as a m1 instead of m. So m1 will be equal to 0.405 plus 0.003 over h plus ha. So that is your equation number 4. So using this formulas, we can quickly estimate the discharge over the rectangular weir. So that's all for this discussion, which was involving the empirical formulas for the discharge over the rectangular weir. In the next section, we will also solve some problems so that you will be much aware that how to use the formula in order to estimate or solve the numerical problems. So in continuation of the previous lectures, now we will discuss the special kind of weir that is called as the Cipolletti weir. The Cipolletti weir is a trapezoidal weir which is defined as the weir which has a side slope of 1 horizontal to 4 vertical, as shown over there. So if we write the definition, that comes out to be tan theta by 2. So theta by 2, so that tan theta by 2 is equal to dc divided by db, and this is already defined as h by 4 over h. So what we can figure out that tan theta by 2 is equal to 1 by 4. So if we take out this value, so this value is coming out to be theta by 2 is coming out to be tan inverse 1 by 4, and that comes out to be 14 degree 2 minutes. So that is the slope which is provided on the both side of the trapezoidal weir, and that's how what exactly happens is that by providing this kind of slope, an increase in discharge through the triangular portion of AEF and BDC of the weir is obtained. So if this slope is not provided, the weir would be a rectangular one, and due to the end contraction the discharge would also decrease. So what we can say that in case of the Cipolletti weir, this factor of end contraction is not required. So what we can say, by providing a slope of 14 degree 2 minute on the both side of the trapezoidal weir, we are just compensating the loss in the discharge which might happen due to the presence of a rectangular weir having some end contraction. So that's how this channel becomes efficient. So let's see that how this particular Cipolletti weir works. So the discharge through the rectangular weir with two end contraction can be written as Q is equal to 2 by 3 CD L minus 0.2 H. So 0.2 into 1 multiplied by H, because two end contractions if we are assuming, and multiplied by 2g H raised to the power 3 by 2. So we can again write it as Q is equal to 2 by 3 CD L under root 2G H raised to the power 3 by 2 minus 2 by 15 CD under root 2G H raised to the power 5 by 2. So if you inspect this particular expression which is shown over there, so due to the presence of end contraction, the discharge decreases by this much value, which is 2 by 15 CD under root 2G H raised to the power 5 by 2. So this decrease in the discharge can be compensated by just providing two side slope that discharges through the two triangular portion that is equal to the this particular decrease of the discharge. So what exactly is that? We have to equate that how much discharge is coming from these two portion, and that the summation of the two discharges should be equal to the this particular value which is written over there. So let's start with this one, that the let the slope is given theta by 2, so that is already shown, and the discharge through a V notch of the angle theta, that expression we have already used, that this Q is equal to 8 by 15 CD under root 2G tan theta by 2 H raised to the power 5 by 2. This is the expression we have used for calculating the discharge flowing through the V notch of the angle theta. So now this particular discharge should be equal to that particular value which we are going to compensate. So this value will be equal to the 8 by 15 CD under root 2G tan theta by 2 H raised to the power 5 by 2 is equal to 2 by 15 CD under root 2G H raised to the power 5 by 2. So if we equate this thing, what we will find out is that this will cancel out, CD will cancel out, H raised to the power 5 by 2 will cancel out, and what left is that tan theta by 2 will be equal to 2 by 15 multiplied by 15 by 8, that is equal to 1 by 4. So that's what is the scenario, that theta by 2 is equal to tan inverse of 1 by 4. That value is coming out to be 14 degree 2 minute. So that was the definition of this one, which is proved over there. And that's how the discharge through the separative weir can be directly written as that the Q is equal to 2 by 3 CD into L under root 2G H raised to the power 3 by 2. So it is interesting to note that even the it is a trapezoidal weir, but the discharge is being used as this one. Now if we are considering the velocity of approach into the picture, the same equation can be modified as Q is equal to 2 by 3 CD multiplied by L under root 2G H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. That particular equation we will be using in order to assess the discharge over the Cipolletti weir with the consideration of the velocity of approach. Now in the next section we will discuss some numerical problems, and we will learn how to solve the numerical problems on the Cipolletti weir. Now we will solve a problem which is based on the empirical formula for the discharge over the rectangular weir. So there is two popular empirical formula proposed by the Francis and Bazin. So based upon these formulas, we will figure out the how to estimate the discharge So the problem says that head of the water over a rectangular weir is 50 centimeter, and the length of the crest of the weir with end contraction suppressed is 2.0 meter. So find the discharge using the following formula, Francis one as well as the Bazin's formula. So let's start the solution part. So the given values are this, the head over this is that is your h is equal to 0.5 meter, and the length of the crest of weir with in contraction surface is 2 meters. So L value is 2.0 meter. So the if we use the Francis formula in order to get the discharge over the weir, so the Francis formula says that Q is equal to 1.84 times of L into H raised to the power 3 by 2. So this Q will be 1.84 multiplied by L is 2 and H is 0.5 raised to the power 3 by 2. So if we solve this equation, we will get that Q is equal to 1.30 meter per second. And in the next section, we will solve the same problem using the Bazin's formula. So Bazin formula is somewhat much different, where the involvement of H is more. So the Bazin formula says that Q is equal to M into L into under root 2G H raised to the power 3 by 2. So M is a different constant that is depending upon H itself. So this is 0.405 plus 0.003 over H. So first of all, we will determine the M value. So this will be 0.405 plus 0.003 divided by H value is 0.5. So M will come out to be 0.411. So this is the M value. Now we will figure out this Q value. So Q is equal to 0.411 into L is 2 meter, and then under root 2 multiplied by 9.81 multiplied by 0.5 raised to the power 3 by 2. So Q will come out to be 1.287 meter cube per second. So this is the answer we are getting from the Bazin's formula, and this is the answer we are getting from the Francis formula. So these are very close. However, this M value is dependent upon the head. So that's why this formula is somewhat much different from the Francis formula. So this particular demonstration shows that how to approach for the estimation of the discharge over the rectangular weir. So that's how we used for the in the field. So our next problem is such that where we do have a very long weir, and that is being divided into number of the bays, and using this by using this base we do have subdivided weirs, and using the subdivided weir, how the discharge over the weir has to be determined, that we will solve for this problem. So the problem says that a 45-meter long weir is divided into 15 equal bays by vertical post, and each is 30 centimeter wide. So determine discharge over the weir if the head over the crest is 1.5 meter and the velocity of approach is 2 meter. So let's go for the solution of this problem. So first of all, we will list all the values which is given. So length of the weir, that is we can say that is L1 we can say. So L1 is given us, that is a 45 meter, and the number of bays is 15. For 15 number of bays we need the 11 post. that we can understand that if we have a vs as that, and if this channel is some posts are over there, so let's say there are three posts, so the inclusion of three posts has divided the weir into the four sections. So using the same strategy, now we know that with having a number of 15 base, the required number of post is 14. 15 minus 1. So this will be the number of vertical posts. So width of each post will be, can be determined. So that will be equal to the uh, as the width of the each post is already given in this problem, that is the 30 centimeter. So this is 0.3 meter. Then the effective length of the weir, we can find out that effective length, that is our L, that will be equal to L1 minus a number of posts are, let's say this is n value, and multiplied by the width of the each post. So let's say this is W. So effective length L will come out to be, L1 is 45 meter minus n is 14, and the width W of the each post, let's say this is W, so this will be 0.3. So this comes out to be 14 multiplied by 0.3 is equal to 40.8 meter. Now the head over the crest is already given. So that is our h. That value is I guess 1.5 meter. So 1.5 meter. Now so velocity of approach is also given to us, that is 2 meter per second. So VA value is 2 meter per second. Now having all this such value, we can determine the HA. So HA is equal to VA square divided by 2G. So this value comes out to be 0.2038 meter. Now, so number of end contractions are, so the number of end contractions will be the 2 multiplied by the number of base which has been divided, is that is 15. So the end contractions will, number of end contraction will be 30 here. Now we will use the formula, that is Francis formula for end contraction and the velocity of approach. So the using the Francis formula for this estimation of Q, that says that Q is equal to 1.84 multiplied by L minus 0.1 multiplied by N multiplied by H plus HA, and then again in bracket H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. So let's put all the values. So Q will be 1.84 in bracket. L value is given to us, that is 40.8 minus 0.1. Now n number of end contractions are that is 30. This is 30, and the H is given to us. H is 1.5 meter. So 1.5 plus HA is 0.2038, and then bracket close, and then so 1.5 plus 0.2038 raised to the power 3 by 2 minus 0.0 sorry 2038 raised to the power is 3 by 2, 3 by 2, and then bracket closed. So once we solve this Q value, So this will give the answer of, so calculation gives that Q is equal to 139.92 meter cube per second. This is the our answer. So our next problem is also where the weir with end contractions are available there, is there. So it is interesting to note over there that instead of figuring out the discharge, this problem asks for the possible number of the openings with given the discharge value. So let's go for the solution of this problem. So problem says that a discharge of 5000 cubic meter is passed over a rectangular weir. The weir is divided into a number of openings and each of a span of 10 meter. If the velocity of approach is 5 meter per second, find the number of the openings needed in order to head of the water over the crest is not exceeded by the 3 meter. So the Q value is given to us. So Q is 5000 cubic meter per second. No. So number of length of the each opening 10 meter. So we can say the length of each opening. Length of each opening at L is 10 meter, and the next that VA value is given to us, that is 5 meter per second, and the head over the weir that is required over here is 3 meter, so that should not exceed by the 3 meter. So H is required is 3 meter. Now everything is given to us. With this values we can go for the solution of this problem. So we have to figure out the number of openings. So let's say that number of opening is n. Number of opening is n. So using this particular approach, we will figure out what is the HA value. HA value is V square divided by 2G, and this will give us the 5 square divided by 2 multiplied by 9.81, and this will give the answer of 1.27 meter. Now there is an important point that for each opening the number of end contractions are 2. So for this problem, the discharge for each opening considering the velocity of approach can be given by the Francis formula. So Q is equal to 1.84 multiplied by, in brackets, L minus 0.1 multiplied by 2 in brackets H plus HA, and then over H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. That particular formula is used for the estimation of the discharge. So we can put all the values. So Q is equal to 1.84. L is our 10 meter. 10 minus 0.1 multiplied by 2, so this is 0.2, and H is given to us is 3 plus HA is, we find out 3 1.27, bracket close, then this is 3 plus 1.27 raised to the power 3 by 2 minus 1.27 raised to the power 3 by 2. So if we solve this thing, the answer will be coming out to be Q is equal to 124.4 meter cube per second. So that is the discharge we are getting from each opening considering the velocity of approach. Now in order to get the number of opening, the total discharge, it is already given to us, that is the 5000, and this discharge is coming from the each opening. So in order to get the number of openings, that is the n, we have to do the total discharge and then the discharge which is obtained from the each opening. So this value will be coming out to be total discharge is our 5000 divided by 124.4. So the answer will be 5000 divided by this is nearly, the answer is coming out to be 40.2. So we can say that this is nearly the 40 number of openings is there. So number of opening is 40. So this is our answer. Next problem we are considering is related with the Cipolletti weir. So the question says that a Cipolletti weir of the crest length of 0.8 meter discharges the water. The head of the water over the weir is 0.4 meter. Find the discharge over the weir if the channel is 0.95 meter wide and 0.65 meter deep. So let's start for the solution of this particular problem. So first of all we will write down all the values which is given to us. So the CD value is already given, that 0.6, and length of the weir that is given to us is 0.8 meter. So L is length of the weir, that is 0.8 meter, and then head of the weir, so H value is 0.4 meter. Now the channel depth is also given us which is 0.6 meter. So channel dimensions such that the channel width and depth of flow. So depth is 0.6 meter and channel width is 0.95. Please excuse me, this is not 0.95 centimeter, this is 0.95 meter. Now, so if we solve this problem, so the area of cross section of the channel, that is A, can be written as 0.95 multiplied by 0.6. So that's come out to be 0.57 meter square. Now, so the velocity of approach will first will determine the discharge over the weir. So Q value will be for this particular weir is 2 by 3 CD multiplied by L multiplied by under root 2G H raised to the power 3 by 2. So if we put all the values, we will get the Q value. So Q value is coming out to be 2 by 3, CD is 0.6, L is given to us, so L is 0.8 and multiplied by under root 2 9.81 multiplied by H raised to the power 3 by 2, so H is 0.4 and raised to the power 3 by 2. So if we simplify, this Q value will be 0.360 meter cube per second. That is the Q value. Now using this Q value, we can figure out the VA. So VA is equal to Q over A. So Q is 0.360 and A is 0.57. So this gives a value of 0.63 meter per second. Corresponding to this HA, we can figure out, so this VA value, HA, we can figure out that VA square divided by 2G. So this value is coming out to be 0.020 meter. So that is the HA. So now using the discharge equation, what we can write that Q is equal to with inclusion of approach velocity 2 by 3 multiplied by the CD multiplied by L under root 2G H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. and then bracket close. So let's put all the values, and after putting all the values we can get q value as, so the q value comes out to be 0.3841 meter cube per second. So that is our answer.